In this video, I want to show you the mathematics of a quite interesting problem, in particular, among all the closed curves in 2D, so in 2 dimensions, we want to find the curve which encloses the greatest area. With some kind of intuition, it's quite straightforward to understand that the curve that we are searching for is a circumference. But I want to show you the mathematics behind this because it's quite interesting and it might give you some important insights to be used and applied to other problems. So let's start from a curve in 2 dimensions written in parametric form. It means that we can write, for example, x1 equal to f of t, x2 equal to g of t. And the parameter t is a parameter which is between 0 and 2 pi. When t goes from 0 to 2 pi, we travel along the curve from the initial point to the end point, and the initial and the end points coincide. We have the constraint, the following constraint. So the integral from 0 to 2 pi of f prime squared plus g prime squared to the power of 1/2 dt, this is equal to the length of the curve. It's quite trivial because the length of the curve is given by an integral over ds, where ds is the element of the curve, and ds is simply equal to the square root of dx1 squared plus dx2 squared. And when we parameterize the curve with respect to t, we can write, of course, this integral here in this fashion. Let's go on. We need to write the area of the curve. We can write the area of the curve in the following manner. We have to maximize the area, so we are going to write an integral over a closed curve, so I'm going to write it like this, of x2 dx1, because x2, if you want, is like the y coordinate, whereas x1 is like the x coordinate. And as we move along the curve, so let's sketch a generic curve like this. So this is the axis for x1, this is the axis for x2, and dx1 is a small increment along this direction. It is something like this, and then we multiply by x2. So it means that we are summing over all these small areas here. And for this dx1 here, this positive dx1, we also have another value for x2, which is this other portion along the curve. And as we move along the curve and we sum over all these small portions, these small areas, we get the overall area of the curve. Our aim is to maximize this integral here, but remember that we also have a constraint, and the constraint is that we keep the perimeter or the length of the curve fixed. So we can rewrite our problem by using Lagrange multipliers, and in a particular way. So we're going to rewrite our problem like this. The integral x2 dx1 can also be written as integral g of t f prime of t dt, and we have to integrate from 0 to 2 pi. So this was the integral over the closed curve. And we can rewrite the problem like this: integral from 0 to 2 pi g f prime, and then we have to keep track of the constraint. So we have lambda, which is the Lagrange multiplier, and this multiplies the following function: f prime squared plus g prime squared to the power of 1/2 dt. So this is, if you want, our Lagrangian now. We are going to rewrite our problem in terms of a Lagrangian, and the Lagrangian depends on the variables gf and also g prime f prime. And you can see that actually there is no dependence upon f because it does not appear here. But for a general problem, the Lagrangian can be written in this form, and then we can write Lagrange equations in order to find our fundamental equations. Remember that we need to maximize this integral here, and we have also to keep track of the Lagrange multiplier. This is a Lagrangian that also keeps track of the constraint, because we have added lambda multiplied by the following function. So we are keeping track of the constraint according to the theory of Lagrange multipliers. Now we can write Lagrange equations, and we have two equations because we have the variables g and g prime and f prime. So we have the first equation d over dt dl dg prime equal to dl over dg, like this. And dl over dg is just equal to f prime. So this is one equation. And you can also integrate this. So you can get rid of this d over dt by integrating over time. And here you will get f when you integrate. Then you just have to calculate dl over dg prime. So you can rewrite that as f minus c2 equal to lambda g prime f prime squared plus g prime squared to the power of minus 1/2, where c2 is just a constant. After we integrate over dt, we are going to need to keep into consideration this constant c2. Then you have the other equation, d over dt dl over df prime equal to dl over df. dl over df is equal to 0, so it means that this derivative here will just be a constant. So you can write the other equation in this form, g minus c1 equal to minus lambda f prime squared plus g prime squared to the power of minus 1/2. So you can write it in this form. C1 is just a constant. So you can get here simply by considering the following. dl over df prime is equal to the constant C1. Then you take the derivative of L with respect to f prime, and you simply recast the equation in this form. It can be done, it's quite simple. So we have two equations, this one here and this one here. And now what we are going to do is we are going to square both sides of the equations and we are going to sum them. And if you do so, the equations that you get is g minus c1 squared plus f minus c2 squared is equal to lambda squared. And what is this? This is the equation of a circumference. And in this case, you can see that the constants c1 and c2 do not play a major role, since their variation only produces a translation. So it doesn't change the shape of our curve, which is a circumference. The multiplier lambda, on the other hand, must be such that 2 pi lambda is equal to L, which is the length of the curve, the length of the circumference. And this is quite easy to realize because you can see that the circumference here has a radius equal to lambda. So 2 pi lambda is equal to the length of our curve, right? And remember that L can also be calculated by using the formula from before, integral from 0 to 2 pi f prime squared plus g prime squared to the power of 1/2 dt. We need to complete this kind of problem, and we have to show mathematically that by perturbing the circumference, that now we will assume to have a radius equal to 1 for simplicity, so lambda will be equal to 1 for simplicity. We need to show that if we perturb the curve in such a way that the length of the curve remains the same, we want to show that the area will decrease. So it means that basically we want to show that the area is maximum if we consider a circumference. Here, if we consider Lagrange equations, it means that this is the curve which extremizes the action. So the action is the integral of the Lagrangian dt. But we want to make sure that this is actually a maximum, not a minimum. And it's a nice exercise to do in order to improve our own insights and understand much better the mathematics behind. We are going to do this by writing the equation for a circumference, and we are going to rewrite it in this form. So x0 of phi is the function which describes the circumference. So it will be a vector x with two components, and this is equal to x0 of phi. Now we are going to perturb the circumference, so we are going to rewrite our problem like this. We are going to multiply this by 1 plus f of phi. So f of phi represents the perturbation on our circumference. Of course, it will have to be small, and in particular, we are going to assume that this function f of phi will have to be periodic with period 2 pi, because we are considering a closed curve, and in particular, this is a circumference, which we are just perturbing. So we are going to assume that the function f is periodic with period 2 pi, and we are going to assume that the maximum of the absolute value of f of phi, and phi of course is a value between 0 and 2 pi, would be much smaller than 1, and similarly for the maximum of the derivative of f of phi. That's an assumption. There are some technical reasons why we should do that. I'm not going to get into all the details, but it's quite intuitive. And we are going to symbolically represent this function here, the maximum of f of phi, so this value, like this, with two straight bars. So let's say maximum of f, like this, and also f prime with these two straight bars should be much smaller than 1. So it means that the maximum of f prime should be much smaller than 1, the maximum of the absolute value of f prime. Now we need to calculate the length of this new curve. The length of the curve, of the perturbed curve, so it will depend on f. The length will depend on the function f, which is the perturbation, can be written as an integral from 0 to 2 pi of mod dx d phi, and then you integrate over d phi. You can also rewrite this as mod squared and then take the square root if you want. So you have to use this function, this expression here, this vector function if you want. We know that the mode of x0 of phi is equal to 1 by definition, because x0 is the unperturbed circumference. And we also know that the derivative with respect to phi of x0 is equal to 1, because dx0 d phi is the unit vector which is tangent to the circumference. So it's also equal to 1. Also, the dot product between x0 and x0 prime, this is equal to 0 because they are perpendicular to each other. By keeping this into consideration, you can rewrite L of f like this. It's an integral from 0 to 2 pi, and then here we have the square root of 1 plus f squared plus f prime squared, and then d phi. We can impose the condition L of f equal to 2 pi, but only up to infinitesimals which are of a greater order of magnitude with respect to mod f squared and mod f prime squared. So these are the bars which take into account the definition that we considered earlier. And let me just say, when I mention this, let me just say mod f squared and mod f prime squared, but you just have to remember the definition for these straight bars, these two straight bars. Okay, we are going to rewrite 1 plus f squared plus f prime squared under the square root. We are going to approximate it. So this will be approximately equal to 1 plus f prime squared over 2. So I have used in particular the following expansion. So the square root of 1 plus x is approximately equal to 1 plus 1 half times x minus 1 over 8 x squared. From here, from this equation and also this equation here, by considering this expansion, we can write integral from 0 to 2 pi f plus f prime squared over 2 d phi equal to 0. So this is what we get. Now, since f is periodic with period 2 pi, we can use a Fourier series expansion. So f of phi can be written as a0 plus summation with index n going from 1 to infinity, an cosine of n phi plus bn sine of n phi, like this. And of course, if we take the derivative of f of phi, we get summation over n from 1 to infinity. Here we have minus n an sine of n phi, and then we have plus n bn cosine n phi, like this. And now we can calculate the integral from 0 to 2 pi of f d phi. It's quite easy to write it if we use the Fourier series expansion. This is 2 pi times a0, and also the integral from 0 to 2 pi of f prime squared d phi. We need it because we have the following integral to calculate. This is equal to pi times summation over n from 1 to infinity of n squared times an squared, and then we also have plus bn squared, like this. Now, if we replace these results in this expression, what we can write is the following. So we can write a0 equal to minus 1 over 4 summation over n from 1 to infinity of n squared an squared plus bn squared. Now we can calculate the area enclosed by the perturbed curve, and we will use polar coordinates in this case. So we can write in general an integral like this. In polar coordinates, an area can be calculated as rho d rho d phi. So you have to integrate over rho and over phi. And if you carry out the first integral over rho, you have to calculate integral of rho squared over 2 d phi. In general, rho in this case would be the radius of the circumference if it were unperturbed. So it would be the norm of x of 0, which depends on phi, squared. And we know that it is equal to 1. But in general, we should replace this with x of phi, which is the perturbed version of the curve. So if we do that, what we get from here is integral, in particular 1 over 2, integral of 1 plus f squared d phi, and we have to integrate from 0 to 2 pi, of course. This can be written as pi plus integral from 0 to 2 pi of f plus f squared over 2 d phi. And now we can use this formula here to rewrite this last integral that we found. So we can rewrite this as pi plus 1/2 integral from 0 to 2 pi f squared minus f prime squared d phi. Now, for an unperturbed curve, pi would be exactly the area of the circumference, because remember that we set the radius equal to 1. So a of f, the area of the perturbed curve, minus pi, will give us the variation of the area. And this is equal to 1/2 integral from 0 to 2 pi f squared minus f prime squared d phi. But now we can calculate the integral of f squared by using the expression that we wrote earlier, the Fourier series expansion, and also for f prime squared. We can do both of them. And the integral from 0 to 2 pi of f squared d phi is equal to pi times 2a0 squared plus summation over n from 1 to infinity an squared plus bn squared. And a0 squared is actually negligible with respect to this summation here, because if you remember, a0 was of the order of an squared and bn squared, and on the other hand, an and bn are related to the function f, if you recall. So if we square them like this, they will be related to some kind of integral of f squared. Therefore, a0 squared actually falls within the group of terms that we are neglecting, and therefore we can neglect a0 squared from this expression. We already have the formula for integral from 0 to 2 pi f prime squared d phi. I wrote it earlier, and therefore we can find a way to express this integral here. So this can be written as minus pi over 2 summation over n from 1 to infinity, n squared minus 1. And then I have an squared plus bn squared. And you can see that the perturbation produces a decrease in the area as long as at least one of the Fourier coefficients with index n greater than 1 is not equal to 0. We have not examined or investigated all the possible cases. In particular, if the terms with the n greater than 1 are all 0, it means that the function f can be written in this form: a0 plus a1 cosine phi plus b1 sine phi. In this case, the perturbation a of f minus pi, in this case it is of greater order with respect to the second one. So regarding the expansion of the square root of 1 plus x that we considered earlier, we have to add actually other terms. So in particular, in this case, we should write 1 plus 1 half times x minus 1 over 8 x squared plus 1 over 3 factorial 3 over 8 x cubed minus 1 over 4 factorial 15 over 16 x to the fourth power. And we have to use this formula in order to expand 1 plus f squared plus f prime squared to the power 1 half. So you can rewrite this, of course, as 1 plus f squared plus 2f plus f prime squared, and this is x. So you have to expand this and consider high order terms, but we will not do it. I mean, it's quite nasty. I don't want to do it now. But you can show also for this case that this perturbation is actually negative, just like here. So the important thing to notice is that this perturbation is less than 0. If here we assume that there exists at least one term with n greater than 1, which is non-zero. So then we can say that this is less than 0, of course. You can simply see it from here. So if the perturbation is less than 0, it means that the area will decrease. Therefore, the area that we found, actually the curve that we found, the circumference, is the curve which encloses the greatest area.